Because of some internet problem, I couldn't capture the entire video in one go. So let us continue from here. We have come across the iminium ion and the oxonium ion in the formation of imine and during the formation of acetal respectively. What this PPT tells you is there is a common analogy till certain point of mechanism or till certain point of mechanism, and from that point onwards the two pathways differ. There is one strong concrete reason for the divergence of that particular pathway. So here what we will try to find out is what is the common part with this particular mechanism, and what is the difference, and what is the reason that these two pathways are getting divergent from each other. So this is something that we have already learned while acetal formation and while imine formation. This is just a repetitive thing for you all. As you can see here, I have one particular reaction running as acid catalyzed imine formation. Here I have a second reaction running as acid catalyzed acetal formation. Precisely the reaction mechanism have been depicted here. And as you all know that the reactions are acid catalyzed, you will observe that protonation and followed by a good living group as a common characteristic feature. Since this first reaction is imine formation reaction, you have a reaction taking place between the ketone and the amine. As we have already seen before, when you have this particular type of reaction, this is a sufficiently electrophilic, this is sufficiently nucleophilic, and there is a simple electrophile nucleophile reaction, and at this particular stage, there is no requirement of addition of acid catalyst. So when you have this particular attack being formed, naturally there is the formation of new bond between this carbon and the nitrogen. As you can see here, the pi electrons are shifting on the oxygen, making it O minus, and in the process, nitrogen acquires the positive charge. In the next step, this hydrogen or the proton H plus will shift on this O minus so as to give you this intermediate. If you remember, this intermediate is typically called as hemiaminal, okay, and from here onwards, you have your H plus to play an important role. So if I just consider this intermediate structure, what I can observe is it's a tetrahedral intermediate which has formed. But if I see the decomposition of this tetrahedral intermediate perspective, I cannot find any good living group. So it is in order to make this OH into a good living group, H plus is needed. So when H plus is added into this particular reaction, it will protonate this O, oxygen, and will convert it into OH2 plus, and thus making a good living group. Since this group is departing, in order to satisfy this carbon, the lone pair on the nitrogen will come down so as to generate a double bond between carbon and the nitrogen, and thus the compound is belonging into the class of, or rather the reaction is from your imine formation category. Since this nitrogen still holds this positive charge, it is called as iminium ion. Okay, it is called as iminium ion. As we all have already done, the next step of this iminium ion to imine formation, it would be the loss of this H plus so that I can get my imine as the product. So this is when I have acid catalyzed imine formation, this is my intermediate hemiaminal. Here onwards, the H plus comes into the picture and I get iminium ion formation. Let us go to the second reaction, that is acid catalyzed acetal formation. If you remember, this particular reaction covers the reaction between your aldehyde and ketone with the molecule of alcohol. So what I have is I have a ketone, and in the beginning itself, your acid will react with this ketone and convert this oxygen to be a more and protonate this oxygen so as to increase the electrophilicity of this particular carbon. Once this electrophile is generated, then a nucleophile of alcohol will react with itself. So the mechanism is acid catalyzed acetal formation that we are talking about. It will react with the alcohol, and alcohol serves as a nucleophile and will attack this sufficiently good electrophilic center, because of which His pi electrons are shifting on the oxygen. Thus, you are having a new bond which is formed between this carbon and the oxygen. Here, see this bond which has been formed new, and then what you get is positively charged oxygen. In order to neutralize this positive charge, this particular bonded electrons will shift on the oxygen and it will give you this particular tetrahedral intermediate. This hydrogen, either this hydrogen or the added H plus, will serve as the catalyst. It will protonate this OH, converts it into OH2 plus, which acts as a good leaving group. In order to manage that, the lone pair of electrons from the oxygen will come down, will generate the C double bond O bond with the positive charge on the oxygen, and that particular structure is nothing but your oxonium ion. So if you observe now these two reactions parallelly, you will observe that the intermediate which you have is tetrahedral intermediate in both the cases. This tetrahedral intermediates do not have a good leaving group. Thus, you need acid catalyst which will protonate this OH, convert it into OH2 plus, which would be easily decomposed into either your iminium ion and your oxonium ion. So till here, your imine formation and acetal formation bears the same analogy and has all the features which are common characteristic features. From here onwards, the reaction differs. The reason being, iminium ion which has formed will behave as an acid because it has got this hydrogen present on the nitrogen which can be easily donated, and thus iminium acts as an acid, whereas oxonium is devoid of this hydrogen on presence of oxygen, and thus it will behave as an electrophile. So once the iminium ion is formed and once the oxonium ion is formed, the difference in the reaction is because of difference in the structure of these two ions which have been formed. One behaves as an acid and the other behaves as an electrophile. I'm just reading this particular paragraph which has been written. Up to this point, the two mechanisms follow a very similar path with the clear analogy between the intermediate and hemiacetal, that is this hemiaminal and hemiacetal, and similar analogy between iminium ion and oxonium ion. Here, though they diverge because the iminium ion carries a proton which the oxonium ion doesn't have. The iminium ion therefore acts as an acid, losing the proton and become the imine, whereas oxonium ion on the other hand acts as the electrophile, adding another molecule of alcohol and forms the acetal. Okay, so let us go to the next slide where you will be able to see this particular paragraph being converted into your reaction. Okay, so let us go to this slide. You have iminium ion and you have oxonium ion. This iminium ion, as we all have done, this is acting as a acid, so it will give away its proton, and thus you have a conversion of imine. In case of oxonium ion, as we have said, it is behaving as a electrophile. This carbonyl carbon behaves as an electrophile because in order to neutralize this O plus, the positive charge on the oxygen, this pi electron will shift, and this particular pair of electrons will attack here. Okay, so it behaves as an electrophile, and thus it ultimately gives you the acetal formation. So this is very, very important from your exam point of view. So both the reactions that we are considering under the broad heading of nucleophilic substitution reactions of carbonyl carbon replacing carbonyl oxygen, both these reactions proceed with the same mechanism. Both these reactions proceed with the same analogy till the iminium ion and oxonium ion formation, and onwards they differ because of their characteristic structure. One behaves as an acid, other behaves as a electrophile. Okay, so this is something that you have to take into account. Now you may have a doubt that if this behaves as an electrophile, why this is not behaving as an electrophile, right? There is a scope that even this can behave as an electrophile. You have those reactions mentioned in the Claydon where this behaves as electrophile, but since those are not there in your syllabus, let us restrict our discussion only to this particular fact that for us, iminium ion is acting as acid oxonium ion is acting as a base. Okay. So this is something which is important for you from your justification point of justification sort of question. Okay, let us go to the next. That is imines and enamines. What is the difference between imines and enamines? Earlier we have seen the difference between imines and oxines. If you remember, oxines are also imines, but this R3 group which you have is nothing but your oxygen. Now what I am reflecting is imines and enamines. So how imines are formed? Imines are formed when you have aldehydes and ketones reacting with primary amines. How enamines are formed? Enamines are formed when you have aldehydes and ketones reacting with secondary amines. Okay, I am repeating. Imines are formed when I have aldehydes and ketone reacting with primary amine. Enamines are formed when I have aldehydes and ketones reacting with secondary amine. Now, when I'm saying aldehydes and ketone, keep one thing in your mind that it could be aliphatic, it could be aromatic. Okay. What is common feature in these two? Both of them require acid catalysis and both of them proceeds with removal of water. Okay, so let us have a look on this particular reaction and then I will tell you one major difference between the two as far as your product is concerned. This is my starting material ketone. When I'm reacting this ketone with the primary amine, as you all can guess the product, this H2 and oxygen will be lost from the reaction as a water molecule and you have this oxygen being substituted by nitrogen and it is attached to argon. So this is your imine. As we said, it is reaction of ketone with primary amine. Reaction takes place with presence of H plus with the removal of water molecule and you have a formation of double bond between C double bond which can be characterized or rather imine which can be characterized as double bond between C and nitrogen, carbon and nitrogen. On the other hand, you have your ketone reacting with secondary amine now. This is your secondary amine. Again, the conditions are same, catalytic hydrogen, removal of water molecule. But if you see the product which is formed is little different. The product which has formed is not having a double bond between carbon and nitrogen, rather it is having a double bond between carbon with the other carbon, right? So there are two things that we are going to observe in the next slide. What is the mechanism or how this water molecule is getting lost? It is naturally that one of the hydrogen is this, okay? It is naturally that one of the oxygen is this, so from where the second hydrogen is oozing out so that you are getting a double bond between two carbons. That is the first thing that we will going to see. So basic difference between your imine and enamine is imine contains C double bond N, enamine contains C double bond C. So let us go to this. As the name indicates, enamine combines the two features that is in and amine. Now you all know in is when you have a C double bond C and thus in your enamine you have C double bond C double bond being obtained. Okay, so let us consider this particular reaction. This is you have your isobutyraldehyde reacting with the secondary amine that is pyrrolidine. This is specifically the pyrrolidine as a secondary amine. These two are reacting in presence of H plus and by removal of water molecule. Okay, and this is giving you the product of enamine. Okay, what has happened now? If you are recollecting the product to be, if you are just observing the product for the product type of questions, then you can see that the double bond has formed between two carbon units and not between carbon and nitrogen. Okay, so this is your enamine. Now let us go to the next point, how the double bond is getting formed between two carbons. Okay, so see this, this is your aldehyde, this is your secondary amine, electrophile, nucleophile, this is our common regular step. I'm not repeating it now. This is the structure which you have formed where the new bond has occurred between your nitrogen and the carbon. Can you see this? The bond has taken place between the carbon and the nitrogen. Then this particular hydrogen would be shifted on the oxygen. So you get this, which will be protonated in presence of acid catalyst, will convert it into OH2 and then it will be departed. Since this particular OH2 is departed, naturally this carbon will be having deficient number of electrons. So this lone pair of electrons from the nitrogen will be shifted down, and you get a double bond between this carbon and nitrogen, which is similar to your iminium ion, okay, or which is similar to your imine. But what happens next is, if you observe this nitrogen now, this nitrogen is positively charged and you have a double bond being raised. So in order to satisfy this nitrogen, this hydrogen is lost, and these two pair of electrons, which hydrogen now, it is beta hydrogen, right? This is alpha and this is beta. So this particular hydrogen is lost, and the electrons which are holding or which are forming the bond will come down, and thus in resonance the pi electrons are shifting on the nitrogen back. So what you are getting is, you are getting the double bond between these two carbons and thus forming their enamine as a product. Now if you again observe, one more important thing here is, if this is my iminium ion, and if I compare this iminium ion with the previous iminium ion, then this iminium ion is not having any hydrogen attached to it. So there is no scope that this hydrogen is getting lost, because you have to have a water removal, right? Okay. So there is no scope for this particular hydrogen getting lost. See, water is getting removed here, but since it is your acid catalyzed reaction, that catalyst also has to be regenerated, right? Okay, so this is not having your hydrogen attached here. It takes up this hydrogen from the next carbon, and thus in that process shifts the double bond from carbon to nitrogen, between carbon to carbon. If I will just show you this, just compare this iminium ion. You have a hydrogen here, which is shifted. See, the scenario is same. Nitrogen is with positive charge, and you have your hydrogen. So in order to stabilize it, this bonded pair of electrons has come under the nitrogen, and this H plus is regenerated. Here, if I compare this particular structure, this is my iminium ion. Again, it is having a positive charge on the nitrogen, but I do not have hydrogen attached to it. Since in order to stabilize this nitrogen, this lone pair of electrons, this pi bonded electrons are going on the nitrogen, and in that particular process, since H plus has to be regenerated, this bond is shifting down, and thus what we are getting is enamine. So this is all about your acetal formation, hemiacetal formation first, then the acetal formation, imine formation, enamine formation. Acetal hemiacetal formation can take place in presence of acid and base. When you have the reaction of aldehyde and ketone reacting with 1 mole of alcohol, it will give you hemiacetal. When in continuation it will react with one other molecule of alcohol, it will give you acetal formation. Okay, so you have hemiacetal, acetal, hemiketal, ketal, all those reactions written with you. All those reactions are nothing but nucleophilic substitution reactions at carbonyl carbon, replacing the oxygen with, wherein your carbon is tetrahedral carbon. In case of imine, it is nothing but a reaction of your aldehydes and ketones reacting with either ammonia or any of the ammonia derivative. The reaction proceeds only in presence of H plus. The reaction loses water molecule, and thus you get the double bond between carbon and the nitrogen. When you have aldehyde reacting with primary amine, it gives imine. When you have aldehyde and ketone reacting with secondary amine, it gives enamine. So even this is the reaction where your carbonyl oxygen, see, can you see? Your carbonyl oxygen has got replaced with this entire thing. Another important part that we all have seen is, during the mechanism, that acetal hemiacetal formation requires the presence of H plus. They can be grouped into the two steps. First step is formation of intermediate, which is hemiacetal. Second step is formation of acetal. Both these steps require the H plus catalysis. H plus catalysis makes your carbonyl carbon a good electrophilic center, and then the nucleophile alcohol will react to it. In case of enamine, you have just a simple reaction between carbonyl carbonaldehyde ketone with the sufficiently good nucleophilic center, that is ammonia or ammonia derivative. It will give you an intermediate hemiamine. Then onward, it comes your H plus into the picture, and thus it completes the reaction to give you imine. Then holds the analogy between the formation of intermediate of imine formation and intermediate of acetal formation, that is hemiaminal and hemiacetal. Both of them will react with H plus and it will give you iminium ion and oxonium ion. So till here the analogy holds good, but henceforth once these intermediates are formed, then the pathway differs, of which iminium ion behaves as acid and oxonium ion behaves as a electrophile. So that's it, which is there in your syllabus. If you sit with the Claydon, you have few more reactions where it depicts how iminium ion also can act as an electrophile. Okay, but those reactions I don't think they are there in your syllabus, so I'm not covering those reactions here. Even this particular topic is very important from your explanation justified type of questions point of view, and it is even important from your predict the product type of questions. The entire reference is from the Claydon, and you may take some of the questions related to it from your previous question bank. So that's it. Thank you.